Computers process billions of raw data points every second, but raw data is largely useless until it is organized. To make sense of chaos, we use sorting algorithms to force data into a usable sequence, and QuickSort is one of the most widely implemented methods for doing this. This diagram shows our starting point, 10 entirely unsorted numbers. To arrange them using QuickSort, we establish strict rules. In the Lomuto Partition scheme, the very last number is chosen as our benchmark. We call this the pivot. Right now, it's 0. The objective is straightforward. We evaluate all the other numbers against the pivot. If a number is smaller, we push it to the left. If it is larger, it goes to the right. Once that sorting is done, the pivot itself drops directly into the boundary line separating the smaller numbers from the larger ones. By continually isolating a pivot and shifting the surrounding numbers based on that single comparison, local adjustments compound. Eventually, the entire data set falls into exact numerical order. Look at our current array. We scan from left to right, checking if any of these numbers, from 7 through 6, are smaller than our pivot, 0. Since 0 is the absolute lowest possible value in this set, the scan confirms that no numbers are smaller than the pivot. There is no internal shifting to do. Because there are no smaller numbers to push to the left, the boundary line rests at the very front. We complete this partition by making the pivot and the first number physically trade places. 7 goes to the back, and 0 moves to the front. 0 is now exactly where it belongs in the final sequence. It is permanently sorted. We leave that sorted 0 alone and split the problem. We apply the exact same QuickSort logic to the remaining unsorted numbers on the right. Finding the correct position for a single number reduces the total unsorted workload. The algorithm simply repeats this reduction over and over. Here is the remaining unsorted sequence. Following the Lomuto rule, the new last element is 7, making 7 our new pivot. To sort this longer sequence, we use 2 tracking pointers. The first is a scout, which scans ahead looking for numbers smaller than 7. The second is a boundary line, marking the exact drop zone for those smaller numbers. The scout looks at the first number, 2. 2 is smaller than 7, so it gets placed behind the boundary line. The scout then moves to 9. 9 is larger than 7, so the boundary line stays put, waiting for the next small number. The scout continues. 1, 5, 3, 4, and 6 are all smaller than 7. As the scout finds them, they are swapped continuously to the left of the boundary line, shoving the larger numbers, 9 and 8, to the right. With the scan complete, we place the pivot into the space designated by the boundary line, swapping the 7 with the 9. The 7 locks into its permanent place. The numbers flanking the 7 are still out of order, but the logic holds. Everything to the left is smaller, and everything to the right is larger. The array is successfully bifurcated into 2 smaller territories. We move to the unsorted cluster on the left. The last number here is 6, making it the new pivot. The scout scans the line. 2, 1, 5, 3, and 4 are all smaller than 6. Because there are no larger numbers to swap around, the boundary line rests at the very end. The 6 stays exactly where it is and is marked sorted. What we are doing here is called recursion. We take a process that worked on the whole array and immediately repeat it on the next nested chunk. We step into the remaining chunk. 4 is the pivot. 2, 1, and 3 are smaller, so they swap to the left. 5 is larger, so the 4 swaps into the middle. Now both 4 and 5 are locked. By calling its own instructions, QuickSort automatically adjusts its logic to fit any size problem without needing BU instructions. We're down to a cluster of just 3 unsorted numbers. 3 is our pivot. 2 and 1 are already smaller than 3, so they stay left. The 3 locks into its end position. This leaves a final partition on just 2 numbers. 1 is the pivot. 2 is larger, so it belongs on the right. They flip into their correct sequential order. The algorithm guarantees success by systematically crushing down the problem space until the final comparisons are undeniably simple. In algorithms, a base case is a mathematical rule that tells the program to stop. For QuickSort, any subarray reduced to a size of just 1 or 0 elements is automatically considered sorted. With our final swap complete, every remaining ungreen element in our timeline has reached this base case. We can now view the final structure. All 10 numbers have moved from a chaotic state to perfect sequential harmony. The core loop we executed is simple. Pick a Lomuto pivot, move smaller numbers left, and recurse on the chunks. Mastering QuickSort doesn't require memorizing the final order of the data. You just have to trust a repeating geometric rule, execute the comparisons, and let the algorithm construct order out of chaos.